So the thing is with this section, we're going to start off, we have series definitions. So I know you've spent a little time with sequences and series in pre-calc. I don't think you did any in calculus. And then we're going to look at geometric series specifically and the geometric series test and the nth term test. So we're going to look at two different tests for convergence and divergence. And chapter 9, the bulk of what's different about AB to BC is doing all these different tests for convergence and divergence. And the trick is you have to understand the circumstances you're given, the sort of environment that you're in. And as we learn more and more tests, I think there's like 8 different tests that we have to learn. It might even be more than that. You have to figure out, when can I apply this test? Do the conditions that exist allow me to determine if I have a specific type of diverging series or converging series? And we'll get way more into that. But today where we got to start is with the basics. And in order to talk about sequences and series, we have to look at the nth term and what the formula for the sequence needs to be. And before we do that, we have some background stuff we have to go through. And a lot of this is on page 193 if you want to have that open. But in case you were unfamiliar with the term factorial, this does not mean n. This means n times the next number less than it, then the next number less than that, then the next number less than that. Okay, so if we start with n and then we subtract 1 from it, then you subtract 1 from this, and you subtract 1 from this, and you work your way all the way down to 1. Okay, and this is a multiplication. It's like we have exponents that allow us to have a more concise way of writing out a giant multiplication problem. We also have factorial. And when you take a probability class, maybe you've talked about this a little bit in statistics, definitely when you take a discrete math class, you'll talk about factorial. I'm going to give you a really quick example. All right, 6 factorial. So this just means 6 times 5 times 4 times 3 times 2 times 1. And you go, well, why do we even bother writing the 1? Well, because that's just the convention. That's how it works. One of the things to keep in mind, if this should ever happen to you, you run into a situation like this, if you get something that says 0 factorial, okay, and I'll try to explain to you how that can happen later, but that just equals 1. It doesn't make sense, right? It should be 0, but if it was 0, then it would knock all these different things out, and we don't want to have that happen. So they just made this rule that doesn't necessarily make sense, but 0 factorial always equals 1. So first example, okay, you're going to see things like this where so in this section, you're going to be doing some things that aren't necessarily related to all the different tests that I was talking about before, because we have to work up to that. So the best way to simplify problems like this is to expand as much as you can. And again, keep in mind that the factorial means you just always multiply this first number by a number 1 less than it, and you work your way down. And so what this would look like, this expansion would look like this, okay? And you can write out as many terms as you want. You don't necessarily have to write them all out. And you'll see why in a second where you know to end, okay? So again, this is n plus 2. Take 1 away, that's n plus 1. Take 1 away, that's n. Take 1 away, that's n minus 1. Take 1 away, n minus 2. And then the same thing with n, okay? What do you notice between the top and the bottom? What does? Exactly. So as soon as we get to n, everything is the same from top to bottom all the way down. And so what we can do is cancel everything out from n on down. And so in reality, what this ends up being is n plus 2 times n plus 1. And so that's going to be helpful as we work through some of these problems later on, okay? But when you're asked to simplify a factorial expression, think about expanding it a little bit until you can figure out where the canceling starts, and then eventually it's going to just work its way all the way down with the canceling, and you'll end up with something, okay? Does that make sense? Okay. Let's talk about the definition of a series, okay? A series is a sum of numbers, okay? So we're just going to take a bunch of numbers and add them all up, and that is the series. Now, a series, you'll hear the word sequence a lot too, and the sequence is just the list of the numbers. The series is the sum of that list of numbers, okay? And so here's what an infinite series would look like. Maybe you've seen this notation before. Hopefully you have. Have you seen this capital sigma notation before? Yeah. Yes? Yes, okay. All that means is a series, the sum of. And what this is saying is the sum of the first term all the way up to an infinite number of terms. Okay, so that's why it said an infinite series. If this was just a number, then we'd have a finite series. And we would have a certain number of terms that we would be adding together. But because this upper limit of the summation, this is called summation notation, the upper limit is infinity. That means these terms will add up forever and ever and ever. And now, here's where we start thinking about calculus concepts. Because normally when we think, okay, if I just add things forever and ever and ever and ever, it's going to just grow and grow and grow and grow. And so the sum is always going to approach infinity. Well, that is not true, okay? And I'm going to talk about some examples of how that can be, because intuitively we think if we just add things forever, it's going to approach infinity. The question is, what are you adding, okay? And so that's where we'll kind of get into this a little bit more. A sub n is the nth term, and this is A sub n will eventually represent a formula for each of these terms. So this is, you go from n of 1, n is 2, n is 3, n is 4, n is 5, n is n is infinity. You just keep adding them up until you either can come up with something or figure out that it's just going to approach infinity, okay? So again, a big part of this first part of this lesson is about getting familiar with the A sub n notation, getting familiar with writing things out in that summation form and in series form, and expanding and understanding what that means, okay? So for example, we've got one like this. This is number 2 in the example. It says, write out the first 5 terms of the series. Now, because it says series, that means we're going to add them. Sometimes what this will be known as is the fifth partial sum. So since this is an infinite series, okay, we're writing only the first 5 terms of the series, adding the first 5 terms together. We're not actually going to figure out what that sum is, but sometimes that's called the fifth partial sum, or whatever the number is, the nth partial sum. So all you've got to do here, it's really simple. The first term is plug 1 in for n. The second term is plug 2 in for n. The third term is plug 3 in for n. Now, most of the time, it will start at 1 and it will go up. It doesn't always start at 1. Sometimes it'll start at 0. Sometimes it'll start at 3. So be careful, watch out for that, okay? But when n equals 1, we're talking about the first term. Okay, so go ahead and do that real quick. You don't have to actually add them, but just plug the first 5 n's in. So here's where we're going to start, right? So everywhere in purple is where I've plugged the n in. So I plug 1 in both places. So this is 1 in both 2, 3, 4, 5. And so I'm just going to simplify this a little bit. So this is 1/2 plus 2/3 plus 3/4 plus 4/5. Plus 5/6. Okay. And now one of the things that happens often with series and sequences is you'll start to see patterns evolving. Because one of the things that we're going to do is we're going to go the other way. We're going to write the definition of the nth term, because this is the definition of the nth term. And so we'll get into that here in a little bit. Now, here are 2 more examples. And this is exactly what we're talking about. I'm going to give you I'm going to give you a partial sum with it expanded out, and then we're going to come up with the formula for the nth term. And there's not always a hard, fast way to do this. You're going to have to look for the pattern. You're going to have to figure out how to turn that into some variable expression that will work for every n. And that gets kind of tricky, okay? So here's examples 3 and 4, okay? And so what it's saying is write an expression for the nth term of the following series. So what we're looking for is something like this for each of these, okay? So I'll let you get that down and then we'll try to figure it out. So on this first one, it might be helpful, maybe not, maybe you don't need to do this, but it might be helpful to write this first one as a fraction, okay? Notice that the top is always 1. So certainly the formula for my a sub n is going to be 1 over something, because this is what we're looking at, right? We want to create a formula so that for n equals 1, n equals 2, n equals 3, that this gives me, for n equals 1, it gets this. For n equals 2, I get this. For n equals 3, I get this. For n equals 4, I get this, etc. Okay? Ellie already spoiled it for us. Hopefully you had already had it. What is the bottom doing with respect to n? Yeah, you are squaring it. So this first one is 1 over n squared. Okay? And
what is a of n?
A of n is the nth term. Okay? In other words, it's the formula. This would be a sub n over here in this example. Any formula, any expression that's next to the summation sign, the capital sigma, is what our a sub n is. All right, now this one is trickier. This one is trickier. Fortunately, we have part of this, right? We should be able to know part of this. What part do we know for sure? 3 where? On the numerator. So I'm going to have a 3 up top. That seems pretty obvious, okay? Now the trick is figuring out what the bottom is and how that kind of works, okay? Now, do you see a pattern to get from here to here, from here to here, from here to here? What's happening? What is that pattern to get from each denominator to the next denominator?
Times 2 times 3 times 4.
Say again?
Times 2.
Yep.
Times 3 times 4.
Okay, so that looks good. So this one times 2, then this one times 3, and this one times 4, and this one times 5. Now, we have to figure out a way to put that into some type of formula, because there is no recursive formula. There is no take this answer and multiply it by the number that's 1 bigger than that. That's not a thing. All right. So here, let me help you with this one, because you're not really used to seeing these kinds of things. All right. If this number here, right, was 1 times 2. If I multiplied the next one by 3, isn't it just 1 times 2 times 3? And then this next one is, it's this times 4, right? 1 times 2 times 3 times 4. What is this? What's happening here? What do we call this thing? It's a factorial, okay? And just to finish it off, to make sure we're good, 1 times 2 times 3 times 4 times 5. Yep, pretty confident it's going to be the factorial. And it starts with 1 factorial, 2 factorial, 3 factorial, 4 factorial, etc. So there you go. Some of these problems are going to trip you up, because this is not a normal way of from point A to point Z, right? There could be, we make a left turn somewhere, and then you make a little circle, and then eventually you get to point Z. But that linear type thinking that we're used to in math doesn't always work as well with these kinds of things. And you don't have a ton of experience with that. And so those of you who are in stats have a little more experience with that, with doing probability, because there's not always a straight direct line to the answer. So don't get too frustrated with this. Accept the challenge, because some of you, could use a challenge in math sometimes. The best way to kind of describe it is when you notice the pattern is we're multiplying and it multiplies by a number that keeps going up by 1, that's your cue that you might be needing to think about factorial. We're going to talk about some other ways to determine terms in a series by multiplying here in a minute, other than factorial, okay? All right, let's look at 2 more, and this time instead of just writing the nth term, we're going to actually write it out as a series with summation notation, okay? 2 more examples. So this time, we're going to write an expression for the following series. So the expression is the a sub n, the nth term, but we are going to put it in the context of a series, which means it requires summation notation. So the first part of this is still the same as what we just did, is can we figure out the pattern, okay? And that's the pattern that's essentially going to go in front of, and actually both of these are this way. Sigma notation is going to be n equals 1. Sometimes they list it as k or h. You'll see a different variable. It doesn't matter. But notice that on both of these, we have the 3 dots, that the ellipses is what those are called. That tells you that it goes on forever. So both of these problems are going to look like this. What we have to figure out is what goes here. That's the nth term, okay? So in reality, these 2 examples are just like the 2 examples that we did, except now we're going to put it within the context. That's really the only difference. All right, so what I want you to try to do, I'm going to give you a minute or 2 to try to come up with the pattern. See if you can figure out what the pattern is with respect to n for each of these, and then we'll go through them together. Overall, I'm seeing good things here, okay? You noticed, first off, on this top, right, that it's n times 2. So when n is 1, 1 times 2. When n is 2, 2 times 2. When n is 3, 3 times 2. So that's good. Now, what you should notice, and here's, again, something you probably haven't spent a lot of time with. This is basically the same thing. I mean, it's not the same thing. It's off by 1. This is just 1 less than this. 1 less than this, 1 less than this. So what you should have had was this. So once you notice this, and then you see that these are consecutive odd integers, I will tell you, consecutive even integers is always 2n. Always. Consecutive odd integers is either 2n minus 1, like this is, 2 minus 1, 4 minus 1, 6 minus 1, or it's going to be 2n plus 1. Okay? Now, if n happens to be an odd number, that's not going to affect this, but it could affect this in terms of position. Now, what do you notice about this one? What's happening? Negative, positive, negative, positive. So you're going to have a negative number involved in this somewhere. Okay? So I'll leave you to that one. I'll give you a hint. How are you getting from one term to the next term? Multiply by negative 3. Multiplying by negative 3. So if I multiplied by negative 3 once, and then to get to here, I multiplied by negative 3 again. And then I multiplied by negative 3 again. Well, we have a trick for shortcut for writing things out when we multiply by the same number multiple times. If you multiply by something, the same number multiple times, we have this mathematical way of writing that out. There's your hint. All right, so one of the things we talked about here, right? We multiply by negative 3. Multiply by negative 3. Multiply, we just keep doing that. Now, let's talk about the 2 is what's messing it up, right? Because so in reality, what I have here, I'm going to expand this out. And this is going to be your way that you're going to start to figure this out. This is 2 times negative 3. Agree? Okay. And then this is negative 6, which is 2 times negative 3 times negative 3. This is all of this, I'll just copy it. Times -3. Agree? We're good on that? So if only we had this way in math to have -3 multiplied by itself a bunch of times. The trick is, what's the first term? Okay, the first term is 2. The number of times that I multiply 3 by is 1 less than the term number. So this is the second term, but I only multiply by -3 once. This is the third term, I multiply by -3 twice. This is the fourth term, I multiply by -3 3 times. Are you with me? Hope is that when you get into that situation that you can start writing this out. Now, the trick is, right, this is 2 times -3 to the 0. There's a little manipulation there, which is 1 less than the term we're talking about, because this is, I should probably put that in parentheses. 2 times 1, okay? There's your formula. 2 times -3, we're just 1 less than whatever our n is. Since I multiplied this one by -3 once, and this was the second term, this is n equals 2. So there's my 2 minus 1, which is 1, okay? Some of you were really close. You were all around it, but you weren't quite sure how to write it. So that's where we land. These ones are going to take you a minute because, again, it's a different way of thinking about it. It's not always going to be a straight line to the place we're going. All right. Let's look at another one. Okay, so example 7, what happens if we add more and more terms of a series like this? So my series is, notice, see what I said, it started at 0. Okay, at 0, it's still the first term. Whatever this number is the first term in the series. The sequence is going to be, write the first partial sum, the second partial sum. And what the partial sums mean is the first partial sum is the first term. The second partial sum is the first and second term added together. The third partial sum is the first, second, and third term added together. Okay? So in this case, obviously the first partial sum, when I take the first term, it's just 1. Okay, so now it says sequence, we're just making a list. So the second partial sum is add these two terms together. Okay, so that gives me 4. Okay. What's the third partial sum? 9. What's happening? What is the fourth partial sum? 16. And fifth partial sum? 27. Well, this would be a 9, right? 25. Okay, it would go on forever, but that is my list of partial sums. And at some point, you should be able to recognize, right? We got another pattern going on here, and I'll explain why that's important.
Wait, why is it 9?
I mean, if we just look at these numbers, 1, 3, 5, 7, 9.
So it's like 2n plus 1.
Okay, so I plug 0 in, that gives me 1.
Sorry.
Remember, so that's 4, because the fifth term is actually n equals 4.
Yeah.
Okay. All right. Anyway, what's going to happen? Because these are the sums. As I keep adding more and more terms to this series, what is happening? What is it approaching? If I did this forever, it's just going up and up and up and up. Right? There is no bound. Boundless. This is like a limit, right? If I keep adding numbers to this to this series, my sums keep getting bigger and bigger and bigger and bigger, and they will continue to grow like that. Okay? When this happens, the sequence of partial sums approach infinity. When this happens, the series is called divergent. Important. important term. This series will diverge. It will not converge. Converge means it's approaching a number, right? That's when we talk about limits. That's what we're talking about. It doesn't necessarily equal that number. It's approaching that number in a limit. If it's divergent, it never approaches anything. Okay? So this would be an example of a sequence that diverges. We're going to talk about convergence here in a minute. And the bulk of chapter 9, that's our theme. Does it converge or does it diverge? And there's lots of different ways to figure that out. All right, got to get moving. So on this one, what would happen if we add more and more terms to this? So I'm just going to write these out for us. So this is, so I plug 1 in, I get 3 over 10. I plug 2 in, I get 3 over 100. I get 3 in, 3 over 1,000, etc. Okay? What's happening to each of the numbers that I'm adding to the next group? So each of these numbers is getting smaller and smaller and smaller and smaller till eventually it's like adding nothing. Okay? When this happens, so when I gave you the premise at the beginning, it seems weird that if we add stuff for infinity, it should always just grow without bound. But sometimes what you are adding is essentially nothing. So the growth stops. And that's when we see convergence. Okay? So we can add forever, but there's a point where we're basically adding nothing onto it, and that growth ends. Okay? And so this is an example of a convergent geometric series. And the reason why it's a geometric series, and here's what the definition of a geometric series is, because we've been talking about it and talking around it, is in order to get to the next term, if you multiply by the same thing every time, then it's a geometric series. So in that example where we had the negative 3 to the power, we were multiplying by negative 3 every single time. That was an example of a geometric series. To get from one term to the next term, when you multiply by the same number, that is a geometric series. Now, I'm going to give you a bunch of definitions and formulas and stuff. Some of them you need to write down, some of you don't, and I will let you know which ones.
Wait, what value would this one converge on? Is it 0 or is it?
Well, we're going to get to what it converges to. So the terms, the individual terms will approach 0. The sum, the overall sum, will not approach 0. And I'm going to show you how to figure out what it actually approaches. We are going to do that today. Okay? So, again, this is just a general form, just basically saying what I just said. And this is important. You have a starting value A, and then you multiply by the R, which is called the common ratio. That thing that you multiply by every single time is called the common ratio. And this is what the general form of a geometric series looks like, right? And this has looked a lot like that example we did. Our first term was 2, then we multiplied it by negative 3, then it was negative 3 to the second, etc. Okay? Now, on the next slide, I'm going to go through a proof to get to the question Jackson just asked. How do we know what the sum is? I'm going to show you the formula, okay? I'm going to show you the formula to come up with what the sum is for a specific type of geometric series. Because if it's divergent, we can't find the sum. If it converges, then we can't find the sum. Now, I don't want you to write what's down on the next page, okay? I'm just going to go through it with you because it's not that important for you to understand. This is really the proof of where the formula comes from. So if I have a series that looks like this, and let's say I just multiplied this by r. Again, don't write it down, just pay attention. Okay? When I multiply this by r, this turns to ar. I multiply this by r, you get ar squared, etc. And what you see here is basically the terms are all the same. So what you can do is you subtract them. If I just subtract this minus this, all of these cancel, except there's going to be a term down here that doesn't cancel. And so what I end up with is just a. All these terms cancel, all these terms cancel. And so what we do here is factor out the s. There it is. That's 1 minus r, and then I divide by 1 minus r. This is the sum of a geometric series if it converges. This is a formula you need to know. A is and I'm going to put this up here. Where is it? Yeah, here it is. Okay, there you go. That's the one you want to have. So A is the first term, and you divide by 1 minus whatever the common ratio is. You use this if the series converges, because not all geometric series are going to converge. And here's how you know when they converge. Okay, and this is the most important part of this. This is the first test, the geometric series test. If the common ratio is greater than or equal to 1, the absolute value of the common ratio is greater than or equal to 1, then it diverges. Just to be clear, actually I'll get there in a second. If the absolute value of the common ratio is less than 1, the series will converge. This means a regular fraction, positive or negative regular fraction. No mixed numbers, no improper fractions, 1/2, -1/3. If R is within 1 and -1, then it's going to converge, okay? Here, so if R is greater than or equal to 1, or R is less than or equal to -1, then it will diverge. Down here, it will converge, okay? And so that example that we looked at with the -3 is in the divergent area, because the numbers kept, even though they were bouncing back from positive and negative, the number itself was growing. When you have a fraction, that your common ratio is a fraction, that's when it will converge. So on that last problem, what were we multiplying by every time? We were multiplying by 1/10. Because every time we went from, it was 3/10, 3/100, 3/1000. So that one was going to converge. And the way that we would figure that out is you would just plug it into the formula. You take the first term, and we're going to go through some examples where we actually do that. I don't want to do that for the first one. Okay. All right. Keep moving here. We're going to go through 3 examples. We're going to try to go, yeah, we're doing okay on time. Determine if these series converge and diverge, and if possible, find the sum. In other words, because at this point all we have is geometric series test. If it's a geometric series and the common ratio is in between -1 and 1, it will converge. Tell me the sum. Okay? So the best way, in my opinion, to do these, to start with, is to list some of the terms out, especially because you're not used to this. All right? So in this case, again, the first term, n starts with 0. So this is 3. 2 to the 0 is 1, so this is 3. Then I plug 1 in, I get 3/2. Then I plug 2 in, I get 3/4. Usually that's enough. What am I multiplying by? 1/2. Okay? We are multiplying by 1/2. R equals 1/2. Is that going to make it converge or diverge? Converge. Okay? So it's going to converge. Now here's the wording that you're going to use, because you got to get used to this. I fear. Yep. So what we would say is converges by geometric series test. That's something you're going to have to start getting used to, because in all these problems that we're going to work on in Chapter 9, you're going to use a test, and a big part of the exam is going to be, okay, does it converge or diverge, and how do you know why? Now, since it converges, we can use the formula to come up with the actual sum. So the first term is 3. The common ratio is 1/2. This gives me 6. So if I could actually add the terms up an infinite number of times, which of course you can't do, it would approach 6. The sum is going to approach 6. Again, think of it like a limit. Questions on that? Let's keep moving. All right, this one. First term, the first term?
1.
What's the second term?
9/4.
Try again. N is 1. 3 over 2.
2/2, then 9/4.
All right. What did I multiply? I stopped. I didn't even do the 9 over. You can put it in there, sure. Put as many terms as you're comfortable with. How do you get from one term to the next term? Are we multiplying?
Multiply by 3/2.
3 over 2. Okay, so R is over 2. Converge or diverge? Diverge. It's bigger than 1. Okay, so we'd say the same thing. Divergent by the geometric series test. Give a reason. 3 over 2 is greater than 1. They always like when you give a reason. All right, gonna keep moving. This last one.
What happens if R is 1?
Then it's divergent. If it's a geometric series. We'll get to when R equals 1, there's going to happen. That happens a lot another time. Okay? This first one, plug 1 in. So it's 4 times negative 1/2. Negative 2. Plug 2 in. I get negative 1/4. Let's just keep going. Plug 3 in. I get negative 1/2. Can you tell what we're multiplying by the formula? What are we multiplying by? Negative 1/2. The formula is giving it away. A, R to the N. Okay, well, it wasn't A. In this case, A is not, our first term is not negative, the 4 was not negative 2. Okay, but when I plug it in, I get that. So my R is negative 1/2. Again, it is converging by the geometric series test. My first term was negative 2. 1 minus negative 1/2. Notice that one there, and I get negative 4/3. All right, we got to get to the nth term test. Here's the thing. Okay. A series cannot converge unless the terms approach a limit of 0. That's what we were talking about, right? As the terms approach 0, that's how the series will converge. If they do not approach 0, they're not going to converge. The nth term test is only a test for divergence. It's the only thing you can use it for. You cannot test it for convergence. This is the test you're going to rely on the most because it's the easiest one out of all the tests. If the limit of my formula does not approach 0, right? Because the limit of the formula has to approach 0 in order to basically eventually add nothing. So if the limit doesn't approach 0, then that guarantees that the series will diverge. If the limit of the formula equals 0, it doesn't guarantee that it's going to converge. So that's why it's inconclusive. The only thing the nth term test is good for is to determine divergence. That's it. And we'll have other formulas that will only determine convergence. Then there'll be other formulas that can do both. Okay, so we just have to watch out for that. So here's an example. Show that it diverges. In order to do that, I just have to show that the limit of this does not equal 0. Okay? Now, so what we're talking about is this. The limit as n approaches infinity of the formula, okay? So the 1 is inconsequential. Right? So if I basically say this grows without bound and the n factorial on the bottom grows without bound, I still have this 2. So this actually, the limit of this is 1/2, which does not equal 0. Therefore, this is divergent by the nth term test. Okay, those are your first 2 tests that we go through that you're going to have to know. And again, these are this one is the easiest one and the best one to test for divergence. Okay, because all you got to do is, hey, does the limit not equal 0? Great, we're cool, moving on.